Welcome back, and this is Chipmaster, and we're going to look at the another demo tutorial on the Apple All-in-One, which is Imac, which is the board number we have here, and I have an image of it also, right? And this is the Imac with the board number 820-3588. Let me just see if I can scroll to the next picture and rotate. Alright, so it's the board number is over here. Oops, it's something too much. Alright, it's at 820, right? 820-3588, and we're gonna look at the timing analysis of this chip, of this board, right? And it uses the Intel Series 8 Gen PCH, which matches the 5th gen or the 4th gen, which is a Haswell and the Broadwell CPU. So here it is, right? So this is the Haswell CPU, right? This is the 5th generation of CPU, as you can see, right? And it is on board, so it's not socketed, right? So this is 5th gen CPU, and here's the PCH, which is the Intel Series 8 SR177 or SR170, which is the HM86 and the HM87, BD82, HM87, BD82, HM86 PCH, as you can see, which matches the 5th generation of CPU, which is the Broadwell, right? Haswell is the 4th generation, right? Haswell comes in a socket, and that's normally found on laptops with the sockets. Right, this is iMac, as you can see, and this, as you know, iMac, this is a desktop platform all-in-one, and it doesn't carry isolation protection, meaning that there's no battery for it to be charged, right? So we're going to look at the timing analysis of the Apple, which is a demo. I won't give full videos, right? My videos are being edited. There are over 600 videos, and the person who's editing them takes a little time, but he's getting them done. So I'll soon have them ready for purchase. Alright, so we're going to look at a preview of this demo video, and I'm going to explain the isolation and protection. There's no isolation protection. Alright, no charging circuits. As you can see, this is the connector. We are 12 volts. For these boards, it uses 12 volts power supply, right? And not 19 volts. It's 12 volts. So the adapter, which is the power supply, which takes the 210 or the 110 volts AC and converts it to 12 volts DC, which is output to produce our standby rails. So I'm going to head over to the schematic now. I already have it open, and here's the schematic, right? And as you can see here, which is the boards at J16LB, right? MLB, right? So this is a iMac. Alright, so first we're going to look at the adapter section, the plugged-in section, sorry. So it's PP, so for Apple they call it PP, right, DC in, right, underscore G3H. Alright, so it's not there, so let's type in PP DC in underscore 12. It's not there. Alright, so let's type in PP. So for the Apple notebooks, it's PPDC in G3H, right? And if you look at the connector at the table of contents here, right, there are different sections you can go. We are looking for the 12 volts input, right? So the table of contents has all that information. So I purposely type PPDC in to show you that there is no PPDC in. The PPDC in G3H is for the notebooks. This is a all-in-one platform, right? So this is 12 volts, and just looking till I find the input supply line. Right, this is, let me just come over here. It's VREG CPU LCD backlight, power rails, right, DDR, signal aliases. Alright, let's go for power rails. Alright, that's on page 70. Alright, power rails, as you can see, we have G3 rails, D3 high rails, we have 1.12 volts PP 12 volts G3H. So this is the rail that we are looking for, and normally this is renamed after coming to a resistor or another conversion circuit. Alright, so let's copy this signal. As you can see, PP G3 PP12 volt G2H SNS, which is a sensing or detection signal, which is coming over to be renamed to become PP12 volt G3 underscore RE GPP 3.42 PP12 volt underscore G3 underscore FET, which is 12 volt S5, and we have PP G2H FET underscore 12 volt S0. So this is an important and crucial part. As you can see, we have a PP 3.42 rail to be powered, we have an S5 rail to be powered, and the S0 rail, which is after the trigger, right? As you can see, so PP12 volt underscore G3 high. The H stands for high, not hot. It's high state, meaning it's high before as you plug in the power supply, right? So it's not hot, it's high, right? So high, and if it's low, it's indicated with an L, right? That's how Apple name their signals. When it's high, it's H. If it's low, it's an L, not hot, right? So we're gonna paste this. I'm gonna just copy this signal first. PP12 volts, which is a sensing signal, a detection signal coming to a resistor, a sensing resistor. So let's take a look. So here it is. Here is a resistor. So PP12 volt underscore G3 underscore H underscore SNS underscore R. After coming through this 0 ohm resistor, which is a sensing resistor, it becomes PP12 volts underscore G3 underscore SNS. Alright, so we're going to take a look at what this is. A sensing circuit, which is reported back information to the SMC, right? Normally this goes to the SMC as a sensing signal, as you can see. And let's copy this signal and see what it has for us. So let me just continue going through the loop here. Alright, and it's going back to where we're coming from, as you can see. So let's copy this signal, which is an R. Alright, just put underscore R. That's a Apple likes to rename their names very consistently and changing the name. So here is our adapter voltage rail. So PP12 volt underscore ABC AC DC. So this is our rail. So it's PP12 volts underscore AC DC. So let's copy this signal, right, and let's paste it. Alright, and this is a table to indicate the pinout. Alright, so here is it. So let's copy here now. So in a nutshell, originally the signal comes from here and then it comes here, right? Right, so this is just the name of the signal they are giving us as a rail, but the official signal is coming from here. Alright, so let's copy this signal. Oops, I didn't copy that properly. Here's the connector. So it's L, so it's J, AC DC connector, MLB to AC DC. So it's converted from AC to DC. And this is the connector J6900 and J6900, which is here. This is J6900. So this is the part that's plugged in from the power supply, right? And this is where the 12 volts enters into the board, right? So this is it. So it's PP12 volt underscore G3, right, underscore ACDC. So this is the common name for the all-in-one Imac 12 volts, right? So it's 12 volts, not 19 volts. Alright, so this 12 volts, as you can see, is going to here. So this is our two important rails. So after producing this 12 volts, oh, I forgot my diagram designer. Let me get my diagram designer. Alright, so here's the diagram designer. So as I draw, as I teach, I normally sketch a diagram. So with a complete step-by-step timing to indicate which steps to check. Alright, which steps to check, and step-by-step timing analysis. So this is a timing analysis of this board, right? And I'm going to explain each step of the way and draw at the same time. Alright, so let's go to the sensing. Okay, so this voltage goes to this resistor, and there it produces PP12 volt, right, underscore G3 underscore SNS, and I've already copied this signal. So that's where it's coming from. So that's the adapter input section, right? So it comes through here, SNS, right, and produces this voltage out, which is going, right? So this is a sensing rail to sense the total system power. Alright, so if any fault on the side, it can cause the system become slow. Right, so it boots up nice and it's slow. The mouse moves very slowly because there's something wrong. So it drops the CPU frequency because these CPUs support the turbo boot technology. So it will drop the CPU frequency in order to put it's a safety mode so that it doesn't create any additional problems. Right, so to put the computer in that state. Alright, so that signal, so this circuit is very important. Right, if any fault with this IC, system will become slow, right, or it's become unusable, freezing, total freezing up. Alright, so the next rail, it's PP 12 volts underscore G3 underscore sense is coming to produce PP 12 volt PP 12 volt underscore G3 underscore REG underscore 3V42 underscore D3H. So this signal is going to produce our PP 3.42 rail, which is the first voltage that should be powered to power the SMC, the RTC circuit, the pull-ups for the SM bus communication and so forth. Right, so this voltage, as you can see, which is PP 12 volts underscore G3H underscore REG. Right, oh, so let me just first sketch the adapted interface. So this is the interface, right, and alright, so we have this output voltage and we have our ground, very important. Right, so our ground is let's put the ground here. Alright, so let's get the electronic signal. Oh, not that one. Alright, so this is ground. I just want to know where I'm at in the alright, so this is our ground point. Alright, so we need ground and we need supply, so I'm just gonna put my input supply. This is my output supply 12 volts line. Alright, so alright, so this will become PP. This is let me go back. I think I copied this one already. Yes, I copied this one already. Alright, here is J6900. I'll put it here. Okay. Alright. This is our adapter in. This is our power supply interface name. Right. Alright, so let's go back to where we're coming from. The PP 3.42. So PP 12 volt is established. So now we need to produce PP 12 volt underscore G3 underscore PP on the underscore REG underscore 3V42 underscore G3H. Alright, so this voltage is going to produce our PP 3.42 volts. So here is it. So as you can see, it's coming through these capacitors, which is coupled, which is becoming not a coupling capacitor. These are known as filter capacitor. So the capacitors connected to ground, it becomes a filter. When it is connected to a signal, it becomes a coupling. Alright, so here it is PP 3.42 G3 hot. Hot means that it is high state. It is generated before pressing the button a power switch, and it is generated immediately as you plug in the SMPS, the switch mode power supply, right? So this is our chip that is responsible to produce PP3.42. As you can see, it has a coil, right? And we have the output voltage, which is PP3.42, and you can see, which is outputting 250 milliamp of maximum output power, right? Which is a very small current, right? And the voltage is 3.42. all right. So as you can see, this chip has an integrated MOSFET because it has a SW, which is the phase output, right? So it has an input, we have a boost. As you can see, it's a PWM chip with integrated upper and lower MOSFETs. So if you use oscilloscope, if you use your oscilloscope and put your oscilloscope at the inductance front end right here, then you will get a lot of waveform right here, pulses, and then on the side you will get a smooth output, right, of a high level of P3.42 volts, which is basically charging and discharging. So this is basically charging the inductor, and it is outputting smoothly with the help of the filter capacitors here, right? As you can see, here is a filter capacitor C6905 is connected to ground. So this is a very important and crucial capacitor. If you remove this capacitor, then the voltage will be fluctuated and cause problems, right? As you can see, there is a feedback circuit RA, RB, which is connected to the feedback to report the output voltage to keep it at a stable voltage. As you can see, there's a reference voltage inside, is 1.25 volts, which is 1 plus RA, right, divided by RB, and it will give you the output voltage, and that voltage should be always 1.25 volts. So if there's any fault with these two resistors, then the output voltage would be abnormal, and therefore the output voltage will be protected and it will stop producing 3.42 because there's a fault with these feedback cap resistors, right? So that's the feedback, that's the beauty of a pulse width modulation circuit. So as you can see, FB, which is the feedback pin, which is connected to measure the output of 3.42 volts, right? And it is monitoring the voltage through these two resistors, right? So this is the formula to calculate it, which is 1.25 multiplied by 1, which is 1 plus RA, right, divided by RB. And this is the formula for any low dropout regulator circuit also. But this is not a low dropout voltage regulator circuit. This is a PWM circuit because it has a switch, we have an output MOSFET, and we have a filter capacitor. So this is a pulse width modulation circuit, right? So let's take a look at the working conditions of this circuit. So when 12 volts G3H comes through this these filter capacitors, come to pin number 6, right? At the same time, this same 12 volts is coming through this resistor R6901 and R6902, which is connected to ground. At the same time, these two resistors are forming a voltage divider, right? So this voltage coming through, and it's coming to PP3 to become PP3 pi. After coming through the voltage divider, it is a partial pressure and it is divided, right? And it is coming to produce 3.42 G3H underscore shutdown underscore L. So as you can see, the L means that this is a low, valid low signal. So when the signal is low, then what will happen is that it will stop outputting PP 3.42 volts, right? So anybody can tell me how many volts is this, right? So let's get the voltage calculator. Let me pause for a moment. Alright, so here's the calculator. So V in, which is 12 volts, as you can see, V in, right? This is coming from this is R1, right? This is R1 and this is R2, right? So the 12 volts, which is V in, right? R1 we have 150k, so that's 150 kilo ohm, right? And R2, which is 49.9k, 49.9, right? And the output voltage is 9 volts. So 9 volts is coming to here and it will conduct, and then the upper and lower MOSFET will start working, right? Upper and lower MOSFETs connected to ground, right? And one connected to the V in pin, right? And the boost, which is connected to the capacitor. As you can see, it has a very small capacitance, 0.22, right? Which is a 16 volts capacitor, and it's a 0.2, right, capacitor, which is a ceramic capacitor. It's connected to the front end of the coil, because what happened that when the MOSFET switches on, the upper MOSFET, the drain spin is connected to 19 volts, right? When the drain spin is connected to 19 volts, it is conducted, so that 19 volts will come to the base of this front end of the inductor. So that 19 volts will be connected to this MOSFET, to this capacitor, right? and at the same time the boost pin, which is integrated of a linear voltage of 5 volts that is generated inside. So the 5 volts is going to be added to this pin, right, and that's going to boost it to how many volts? 24 volts, right, hitting this capacitor. It's charged, so the charge time is fast. So that is why you need a small capacitor here, so the charge time will be very fast. If it's a, say, 4.7 microfarad capacitor here, then the charge time will be too slow, and therefore what will happen, that the upper MOSFET, this chip will burn, right, because the upper MOSFET, the charge time is too slow, so too much, the switch time will be insufficient, so the bootstraps won't work and it will burn this MOSFET and the output will not output, right? So this is a very important and crucial capacitor. If this capacitor is not there, most times you can burn this chip, because the upper MOSFET inside will be out of control in conduction, right, and then it will constantly send in the 19 volt. The lower MOSFET will not switch effectively, so it will burn this chip, the upper MOSFET burn, causing damage, right? So this is this is how a PWM circuit works. All right, so when you get 9 volts here, then the upper and lower MOSFET will start switching and it will produce PP 3.42 volts, right? And this is a very important and crucial voltage to power the SMC, to power the VRTC section, and as it says, it serves as a pull-up voltage, right? So this voltage is very important, and this is a PP 3.42 volts, right? All right, so let's draw. So this is U6900. Right, and it gets the V in. Alright, so PP 3.42 volts is coming out and exit here. Alright, so the output voltage is PP 3.42 volts, G3 underscore REG. Alright, so let's order the steps now, in which we're going to get your normal should check. So this is step 1. And I'm just going to give it a fill color, a line color, red, and next color of a nice deep blue. Alright, so step 1 is producing this one. It should check here. Step 2, which is the input, and that's here. So it's, as I said before, this signal is renamed to a resistor and it becomes this name. And let me save this as Apple 820 hyphen 3588. Alright. Put this on the desktop. Alright. So, oops. So, this voltage is now produced after getting the 12 volts. Right, getting the 12 volts and the upper and lower MOSFET switching working conditions is okay, the feedback is okay, then it will output PP3.42 REG. Right, as you can see, there is no power good. This doesn't have a power good to indicate that the output voltage is okay, so there is no power good signal. So let's go back to the alias page now. So the PP3.42 is generated. Next, it needs to generate PP12 volt underscore G3H underscore FET underscore 12 volts underscore S5. So let's copy here and let's paste. Alright, so here's our 12 volt S5. So S5, which is a soft off, meaning that there is voltage before we switch on the motherboard. Yes. Alright, so this is PP2 S4 S5, as you can see, which is going to generate our 12 volt S5 rail to be converted to 12 volt S0 to power the secondary supply, secondary 3, secondary 5, right, secondary 5 volts, secondary 3 volts, right. As you can see, we have other run supplies for the hard drives, right, keyboards and stuff to get powered. So this is converted to turn on the N channel MOSFETs. So this voltage is very important. The lack of this voltage will cause no display or power down. Alright, so this 12 volt S5 is generated, which is coming to this IC, as you can see. So this is basically like isolator, pretty much. All it does is gets the input, the outputs. There's an integrated MOSFET in it. As you can see, there's a drain, a gate, and a source, right? And we have an on pin, which is the input, right, which is the enable. As you can see, this is SMC underscore PG underscore G2 underscore EN. So this signal is coming from the SMC. So when the SMC gets its working conditions of supply, reset, and clock, it then reads its embedded program, then it will issue this signal immediately, right? So this signal is coming from the SMC, right? As you can see, this is the supply, which is 12 volts coming through this capacitor. It's a coupling, it's a filter capacitor, and it is coming to the, and then we have the enable pin. It will up, and the drain pin is also connected to 19 volts. Remember, this is an N channel MOSFET that's integrated. When it gets 19 volts, then the gate, which is what, 2.4 volts to 5 volts. So when the voltage on the gate is between 2.4, if it's less than 2.4, then this chip will cut off, it will not work. So the voltage must be between 2.4 volts to 5 volts. So this voltage is normally 3.3 volts coming from the SMC, as you can see. So the SMC releases the signal as 3.3 volts, and this is coming to turn on our input integrated MOSFET that's inside of this chip, right? Very important. So 12 volts, right, the 12 volts to the upper MOSFET drain pin, it will conduct, right, from drain to source. It will conduct and it will output. Here is the output, and it will directly output here, right? 12 volts underscore S5 underscore FET. At the same time, we have another MOSFET here, and this is an N channel MOSFET. As you can see, the arrow is pointing to the inwards, and this is an N channel MOSFET, which has an integrated Zener diode inside for any induction or induce and spike that's induced on this line, right? So this 12 volts is coming to here. It will stop here because this is a Zener diode, and you can see the anode. This is the cathode, right? This is the anode side, and this is the cathode side, right? So this drain pin will stop here, this voltage will stop here, the 12 volts will stop here, right? So it needs this gate to be turned on, and as you can see, the gate, which is another drain pin, another gate. So when this voltage will just, this voltage gain will flow from the drain, come through the gate, and it will pull up this voltage, right? And it will conduct FET enable underscore 12 volts. So this is 12 volts coming here. So basically what happened is that this 12 volts that's coming in to power, hold on, all right, so this drain, this D pin, 19 volts coming here to produce conduction with the on pin, then it will conduct this MOSFET, and then at the same time the source will output, right? So this is a nice a very good way of designing this chip, right? So this voltage needs 12 volts. This is an N channel MOSFET, 12 volt S5, and it will output the voltage here, right? And it will produce 12 volt S5. Okay. All right, so let's go over to the drawing section. Alright, so as you can see, this MOSFET, right, so the voltage at the gate is greater than the voltage at the source, so it will conduct, right? So the voltage at the source is 0 volts, so the voltage at the 12 at the gate is 12 volts, so it will conduct full current, and produce PP12 volt underscore S5 underscore F18. Alright, so now so let's so this is 2 and oops. Alright, so this is 2 and this is 3. Alright, so let's go back to the next alias. So 12 volt S5 is enabled. Now PP 12 volt S0 is normally after the trigger. So let's take a look. Well, I can ignore that. So this is after the trigger. That's for later class. Alright, so this is a demo class, so I will not give full information. Alright, so I'll just give you a demo of what I'm having in stored for you guys. Alright, so PP3.42 is generated. So PP3.42, which is this output voltage, right, that is generated from here, from this chip U6900, and it is coming to here, PP3.42 G3H underscore REG, right, and it is going to produce all of these output voltages. Right, they're coming out. This is the output. This is how Apple rename their circuits, produce their aliases. Right, all of these are very important and crucial, so we need it for the SMC power supply, or RTC circuit, voltage referencing, USB mux, and LPC lines, right, and other pull-ups. Right, so let's take a look at the production of this one. Sorry, should be on the schematic. Alright, so this PP3 3.3 is produced, let me just go through, yeah, PP3B3, PP3V3. This voltage is coming to this line. Let's go back. PP3.42 G3H. It's a renamed supply. Yes, it is. Here it is. Alright, so PP3V3. Let's come down. And this is for the fan. Alright, this is what we just did. PP3.42 renamed to be all these. Alright. Okay. Okay, so first let me go back to where we're coming from for the 12 volt S5 rail here. Right, so this 12 volt S5, this signal, I've almost forgotten it. Right, SMC underscore PG underscore G2 underscore enable. Right, this is gonna produce by the SMC. So we're gonna look at the SMC working conditions. So this voltage, as you can see here, is coming from our SMC, right, and this is our SMC, right, and that's U5000, right, LM4, right, FSXAH5BB, right. So this signal is coming from the M2 pin, and this is coming from the SMC. So when SMC gets supply, reset, and clock, and read its program, then it will automatically issue the signal to turn on the 12 volt S5 rails. So here is the main section for the working conditions of the SMC over here, right, U5000, right, this is 2 of 2, as you can see the same, and over here which is 1 of 2, and this is U5000. Alright, so we have VBAT. This is the main supply line for the SMC, the standby power supply name, VBAT, right, and it's coming from PP3V3 SMC, PP3V3 underscore G3H underscore SMC. So we need to backtrack to see where this voltage is coming from. Suppose this voltage is not coming in a, say some liquid came in and threw away in the machine and causing this signal, this voltage not to come. Right, so we need to know where this voltage source is coming from. Then we have supply, and we have reset, which is RST, which is SMC underscore reset underscore L, which is active low. Then we have the clock, which is here, which is SMC underscore external clock, right, and it has and the standby clock, which is OSC0, and we have OSC1, which is a clock, and this is a 12 megahertz clock, right. This is a 12 megahertz clock. So this clock, in the maintenance process, when measuring the working conditions of the standby clock, you will not see a crystal oscillation with the oscilloscope, because in this time, as you have to catch it at a single trigger. When you plug in the adapter or the SMPS, this crystal will oscillate. Once it reaches supply, Once it gets the supply reset clock and read its software, it will stop oscillating until after you press the switch. It will re-oscillate again, right? So that is how this this IC oscillates the clock. It doesn't oscillate during the standby before you press the button. It will come for a few milliseconds and then stop oscillating because it reads the program and configure the GPIO pins. Right, all these pins here are GPIO, right? They need the software for configuration. See, all these PP2, PC, these are all GPIO pins, general purpose input output, and they use the program to configure them because they have different functions for different boards. So based on the board, it has a different function, so it needs the software or the program which is embedded inside to read it. So these SMCs are embedded controller. This is the EC, which is an embedded controller, which is like a small computer, right? It has a clock, it has registers, timers, right, and other functions that's inside, right? So this is the SMC. All right, so let's go backtrack and see where we're getting this voltage from. All right, so this is it. That's one. That's not it. That's not it. That's another pull-up, as you can see. That's not it. Right, PP 3.42 G3H underscore SMC underscore supervisor. SMC supervisor and voltage reference supply. Oh, for the okay. Let's go. This is another pull-up for an SMC. Nope, you can ignore that. SMC G3H is for the switch, the power button, SMC on off L. Alright, this is another pull-up for the reset signal. Alright, this is for the fan. So this voltage is basically renamed coming from here. So it's the same PP 3.42 as you can see. Alright, that's it. So it's PP 3.42 that's generated this voltage. So this voltage is generated from the PP 3.42 regulator here. So it still comes back from here. So it is renamed and then it is called PP3V3. Alright, so let's just go back to where. So it is renamed to that. It's pretty much. Alright. So we have supply. Then the next we have reset. So let's take a look at the reset signal. SMC underscore REST underscore L. Alright. And here is it. Alright, so this is our reset circuit. So U5100, which is a chip that's responsible for the resetting of our SMC. And as you can see, we have a supply line, we have V plus and we have V in, we have reset, we have reference out, and we have a delay, right? Ground and another thermal ground. Alright, so as you can see, we have PPV in underscore SMC, PPV in underscore G3H underscore SMC VREF, right? So this is another voltage, and this is a voltage, which is the PP 3.42 voltage, coming to become PP 3.42 underscore G3 underscore SMC underscore supervisor, which is coming to this pin. So this is the main input line that we need to focus on during the maintenance process, right? So this voltage here is coming to power this one. So as you can see, it says VREF, which is 3.3 R, which is the voltage reference. The voltage detect is 3 volts. So if this voltage is below, so if this voltage PP3V3 underscore G3H underscore SMC is below 3 volts, then you won't get a reset signal. It will pull it low, and this is active low. And if it is low, then the SMC won't release SMPG underscore power code underscore enable to turn on the 12 volt S0 rails, S5 rail, sorry, right? So this is a very important and crucial part, right? As you can see, it's going through a 0 ohm resistor, right? And it is going to pull up by here, which is PP3V3 S0. But if this voltage is below 3 volt, it will pull it to ground, and then the SMC will not get to reset, and it will cause no power, right? So this voltage, which is the voltage detection, the VREF voltage is 3.3 volts and the detection voltage is 3.3 volts, right? So this voltage is very important. So V in coming in here, right? Then the SMC will pull up. Once the voltage here is 3 volts, then it will pass it out, and then at the same time it is pulled up by this voltage, by this resistor, right, R5105, and it will output SMC reset L, which is a high level, right, not low. If it's low, then it will be, the SMC will turn off and won't read its center pin. Now this voltage or delay, which is also a very important, this is coming from our keyboard. So when you press the SMC reset, the command shift and P or and L and a keyboard combination, right, which is a 4-key combination, command shift. So command, right, so command shift, right, I have P and R, right, which is the SMC reset, right, or the command shift. Yes, SMC reset, command shift P and R, or command shift R, which is resetting the SMC. What will happen is that this will pull low. As you can see, it is L at the end, and it will pull low, and what will happen is that it will pull this low, alright, and the EC will reread its internal program, right, and then read the internal program and then restart, right. So that is what the SMC reset L does. This is what this is just a very, this is coming from the keyboard. So let's copy this signal. Most times, alright, this is a 4-key combination, right. Let's copy that signal. Well, it's not used, as the C goes nowhere. So this voltage is low by it should be high level, which is an input which is generated internally high. If this voltage is low, then it will pull this low, right. So this voltage is, this is connected, so it is high, right. So they are connected, right. If you measure out here, it is high 3.3 volts, right. Normally on the Apple machines, the reason why this is not there, because this machine doesn't have a keyboard, right. It uses a USB keyboard. So the USB keyboard has to be plugged in, right. So the USB keyboard is not attached. When you attach the USB keyboard, then through the USB mux, and then it will report to the SMC, right, and then the SMC now through the PCH to the LPC bus, and that signal is sent to the LPC bus to the SMC, and the SMC now will then pull this reset signal low. If it was on a laptop, then this signal will connect to the keyboard, because the keyboard connector is on the motherboard, right. So this one is USB, right. This is an all-in-one. Remember, this is not a laptop, this is an all-in-one, right, MacBook, right. So it's SMC control RTC. We can alright, this one is not really important. So this is our main switch. So yes, so this is it pretty much. So our SMC is resetting, right, getting the PP 3.4 to high. It's not below 3.03 volts. Then it will pull this up, free this line. It will not pull low. So this PP 3.3 will pull up by this resistor and output a high level of 3.3 volts to the SMC, right. So the SMC will be resetted, and this is it, RAST pin, right, and we have a voltage reference also, which is here, right, and it is connected to, see, RBRF, right, see, PP3V3 SMC PP3VC G3H underscore AVREF, which is coming from the same page, and this is an input pin that is coming to here to tell it the reference voltage, right. Very important. A lack of this voltage will cause it not to release SMPG, right here, this signal, very important. So once this SMC gets all that working conditions, this is the first signal that is going to release out of it to turn on the standby rails. Alright, so let me just go to the sketch diagram. Alright, so this is my SMC. Oh, I didn't rename this. I didn't rename that one. Let's use 6970. Alright, and this is our U5000. And this is our SMC. Alright, so we have EBAT, EBAT, which is coming from here. Alright. Now to the next signal, we have our reset. Right, and we have our voltage reference. Alright, next we have our clock. So the clock, which is a standby clock, which is 12 megahertz. Alright, let me just copy our SMC underscore XTAL. Alright, here is it. So as you can see, it's 12 megahertz crystal. Here's a crystal Y5165, right? And this is a 12 megahertz output clock. As I said before, this clock doesn't oscillate all the time. Once you plug in the charger, this happens so fast you have to use oscilloscope to catch this. When the oscilloscope catches the signal, you can see that the 12 megahertz is generated for about a few milliseconds and then stop oscillating until after you press the switch. Right, so that is how it works. So after the switch is pressed, then this crystal will start oscillating again. Alright, so this is the 12 megahertz clock for it. Alright, so let's alright. Oops. Oh. So let me just draw the crystal. And this crystal is Y. And this is 12 megahertz. Reset. Right, and then supply reset and clock, and then it has its internal program. Right, so PC oops, sorry, so EC reads its embedded program. Right, and configure its GPIO pins. Alright, so let's pick a color. I'll put this in red. Alright, so let's order the steps. So this is 5. Alright, so we have here, which is 6, which is the name of this, and that's called the input here. Six, right, 7, right, 8, right, and then 9, which is reading the program, and then it will release SMPG underscore enable. Alright, so this will be 9, 10, sorry. It's 10. Alright, so that's this signal here. Alright, so this is the order. Alright, so this is how the SMC, the working conditions are arranged in the order should check. Right, and it will release the signal to turn on the F0 volts, the S5 volts, 12 volt S5 rail, right? And that's how it works. Alright, so I'm gonna stop here. Alright, so this is a demo. Alright, so this is in paid class you get full timing analysis, as from plugging in the adapter to pressing the switch up till the CPU gets reset signal, and the soft start, how to check the soft start with oscilloscope, how to configure no display faults, right, with oscilloscope. All of that will be explained. Alright, so thank you, and thank you for watching.